Greetings all. Let's talk about solving some logarithmic equations. Now, the next lesson, not this one, but the next lesson, we talk about inverse functions. So here's the big deal with this. When you have an exponential equation, you can rewrite it as a logarithmic equation to solve it. When it comes to logarithmic equations, you can rewrite it as an exponential to solve it. Or it will fall into these different categories. So what I did is I broke this down. You're going to see that I have 3 Roman numerals. So this is Roman numeral number 1 here. Okay, make it dark. Solving log equations that have a single log on one side of the equation. So the first thing you ask yourself is it a property? Because sometimes you will just see something like this. Like log base 8 of 8 to the third equals x. Well, you don't have to show me any work at all. The answer's 3. Why? That's a property. Or they might have something like x equals the natural log of e to the square root of 7. And you go, well, there's not any work to show there either because this is a property. The answer is the square root of 7. Sometimes things are properties. Log base 6 of 1 equals x. It looks like an equation, but guess what? The answer is 0 because whenever you take the log of 1, you get an answer of 0. So sometimes what the equation looks like, it's just a property. You should know it. You show me no work. You move on to the next problem. Now, a little blast from the past. What if it is a mini equation? Now remember, I talked about mini equations in a previous lesson when we were talking about converting and all these properties and stuff. So I have a couple of them right here. I have 3 in fact, because there are 3 log mini equations. There's 3 styles that we work with. So the variable could be like in my first example here, where I would say, dang, you know what? I can trick my calculator into being base 2, but if I don't know what I'm actually evaluating, what do? Well, our trick was to convert. So I could say the base stays the base, the other 2 guys change location, and then this is not a tough problem at all. I could punch this into my calculator if I wanted to. 2 to the negative 3, or I could just realize that, hey, this is just a negative exponent, changes my location, then I'd have 2 cubed, but 2 cubed would be on the bottom. Long story short, the answer would be 1/8. That's the answer you would find on the answer key. Now, I also mentioned that we can do it this way in that previous video because that will cause the x to be all by itself, and then here's the statement I'd be evaluating. So whichever way makes you feel happier, that's what you should go with. Because over here it looks kind of weird if I say I'll do this. But technically, that's fine. I could do that if I wanted to. I am just raising them both as powers to the same base. And remember in mathematics, if the bases are equal, the powers, so we can do it that way. However, some people don't like it when they see the x down there. Whoops. So I'm going to take it away. I'm going to do it this way. I'm going to say the base stays the base. Flip-flop. I'm just going to do it this way. They both work. They're both the same thing. Now, this is the one that most people forget how to do, and they go, dang, I don't know what to do. Well, it's reciprocal power. I take the reciprocal power of that. I take the reciprocal power of that. Heck, we had to do that not too long ago. And then over here, everybody cancels out because it's power of power. I get x to the first, but I don't have to write the 1 in if I don't want to. Whoops, I took away too much. Equals, now once again, 16 to the negative 3/4. Oh my gosh, I made up another example that gives me 1/8 as an answer. I didn't mean to do that, but it is. Remember, this is a root. What times itself 4 times is 16? That's 2. What do you want me to do with that 2? Take it to the negative 3 power. Hey, what the heck? I get 1/8 again for my answer. Could I have punched that into my calculator if I wanted to? Yeah, I could have. 16 to the negative 3/4. So, moving on. Once again, you see that there is a log statement. This is a mini equation, but what unifies all these examples I'm talking about? There is a single log on one side of the equation. That is what all of these have in common. But this guy right here, this dude, this is a trick your calculator style question. I don't know what the log of 17 is, base 5, but I can just trick my calculator. I don't have to rewrite it. It's written in a format that my calculator knows, as long as I know how to trick it. And then I punch it in the calculator, and for all our decimal style answers like this, we're going to round them to the 4th decimal place. So I get 1.76037. So of course I'm going to round this to 1.7604. And that would be my final answer for that question. Now, if it's not a property, let me scroll up. If it is not a property, nope. What if it's not a mini equation? Nope. Well, we're going to do cancel out log style. So take a look at this. This guy looks a little bit more complicated, but you know what? I could just say the base stays the base, flip-flop. I could. Base stays the base, flip-flop. Or I could do it this way. Me personally, I've mentioned this in the previous video. I like doing it this way just because it looks cooler. It looks math, high-tech, smart. And that's always cool. So, if I did it either way, I'd end up with this statement here. And 5 to the 3rd is just 125. If you don't know it, punch it in your calculator. What's it equal? 2x plus 1. I'm going to move this over. And I get 124 equals 2x. And I divide both sides by 2. And 124 divided by 2, 62. So my answer is 62. Let's take a look. See how this one looks? This guy looks kind of funky. But you know what? This is the one where this type of technique, I think, is helpful to visualize. Because not many people go, oh, wait a minute, L, and that's log base E, and blah, blah, blah. But you know what? I call this the monkey one, because you can go E, E, and make monkey noises like that. And then, what do you get? You get this to be an x plus 4. How beautiful. And then E squared. Well, remember, on your calculator, you actually have an E button right above ln. You could take it to any power you want. And if I punch in E squared on my calculator, I'm going to get the super decimal. And that super decimal looks like this. 7 point, oh my God, that's a horrible 7. Let me try that better. 7.38905, blah, blah, blah. But I'm going to round it to the 4th decimal place anyway, so I'm going to stop. But you know what? I'm not done because I need x by itself. So I'm going to take away 4. And then on my calculator, I don't have to line up the decimals like they told me in the 4th grade, because my calculator is going to do it for me. If I say take away 4, what's my final answer going to be here? It's going to be 3.3891, because I would round it to the 4th decimal place. So, take a look at this one now. This one you got to be careful of, because when you learn stuff about solving math equations, sometimes you start thinking, oh, I do it this way every single time. But I want to show you, if you start this one out and you go for this, you go for the bait which is, this is not the way to do it, because you go, well, what do you mean? On this side, it's a property then. And I could say that's 5. What does 5 equal? It equals 6 to the 2x minus 1. Then you go, oh crap, wait a minute. That's an exponential equation. Oh, I know what to do. I'm going to do log base 6 of both sides. And then over here I get log base 6 of 5, which is what I had originally. And over here I'd get 2x minus 1, which I had originally. This I call getting trapped in a circular logic. If you keep doing this, you're going to keep going round in circles. So, if you ever find yourself going round in circles, it's because you missed the off-ramp. Technically, what is this? This is something I can trick my calculator to understand. And that's the thing. Don't get hung up thinking every problem's always going to be the exact same pattern to solve it. Yes, we have seen something like this. Now, log base 6 of 5. I can punch this in on my calculator. I could do log of 5 divided by log of 6. What's it equal? It equals 2x minus 1, which means, what would I be doing then? Well, I would add 1. I would add 1, right? I would take that result, divide by 2. So what I'm trying to get at is this. I could punch this thing in on my calculator like this. I really could. And it will give me the correct answer, because my calculator knows order of operations. But I got to tell you, I would just do it a little at a time. Poco a poco, they say. I would say log 5 divided by log 6. What do I get? I get an answer. What am I going to do with that answer? I'm going to add 1 to it. What am I going to do with that result? I am going to divide it by 2. And if I punch all those keystrokes in one at a time instead of trying to enter everything in at the same time, I'm going to save myself a little bit of trouble, I think. And I get 0.94912, which if I was going to round it off, my final answer would be 0.9491. And I would go home and make some Pop-Tarts, put my feet up, because that would be done. All right. So, before I go to Roman numeral number 2, which is coming up, these are all examples of what if there is a single log statement on one side of the equation. So let's contrast that right away. Let's compare that to Roman numeral 2, which says this. What if you have a single log? So here's my Roman numeral 2. What if you have a single log on both sides of the equation? Now, this is when you can't just convert. Base stays the base. Flip-flop. I can do that because this original problem here had a log only on one side. But here we go. It says single log both sides, raise both sides as a power using the same base number. Why? Because it cancels the logs. That's why. Let's take a look at these two examples here. Hey, if I said base stays the base, flip-flop, both of these guys have a base. See, you can't just convert stuff then. But guess what? We got an easy-peasy solution to this. As long as you do the same exact thing to both sides of an equation, you're not really changing it. So if I do this, I'm going to end up with, on the one side, 3x minus 5. That's sweet. What about the other side? I will end up with 2x minus 3. And then I go, oh, cool. I can move the x's to one side. I can get the numbers to the other side. So what I'm going to end up with is what? X equals 2. And there you go. See, as long as there's a log on both sides, it doesn't matter what log base it is. See this next example? It's got natural logs on both sides. Okay, big deal. This is the monkey trick. E, like a monkey. And what happens? Those are gone. X squared equals 5x plus 6. And then you go, oh, dang, it's a quadratic. Or maybe you don't say that, but I do. I go, dang, that's a quadratic. I have a power of 2, which means I want the highest powered thing positive. I've got to move all this stuff over here, so I'm going to subtract it, which gives me x squared minus 5x minus 6 equals 0. And then we go x and x. Let's try a plus 1 minus 6 situation out on this thing. I think that's going to be the ticket. And I end up with -1 for an answer, and I end up with 6 for an answer. I go, okay, cool. I got -1 and I got 6. There's my answers. Let's continue. What? This looks like the same question. It does. Look, here, I wanted to make these two look real similar to each other. But I did one subtle difference. I made this base 3, not base E, and I changed the 5x plus 6 to a 5x minus 6. So here's my one word of advice. Be real careful when you're working with this kind of stuff, because this time instead of E, excuse me, instead of E, I'm doing 3. And what happens? I get x squared. What's it equal? 5x minus 6. Well, guess what? I'm still going to set this thing equal to 0. Oh, well, I'm going to get the same answers I got last time. No, you won't. Because when you rewrite this one, you don't have the same trinomial, so it's not going to factor the exact same. You can think that, but it is definitely not true. So here we go. Let's break this guy down and say, well, that would be x and x. It looks like -2 minus 3. So I have an answer of 2, and I have an answer of 3. So here's the deal with this. I can get different answers. I can get more than one answer. It's okay. Now let's look at the thing that people mess up more than anything else that I teach all year. Okay, it says Roman numeral 3. Roman numeral 3, more than one log on either side. Okay, when this occurs, you must use laws of logs to rewrite the equation so that it resembles single log form. Okay, this is the most frequently broken rule, so please be careful. Let me show you what I mean by more than one log on either side. Here's my first example that I'm going to walk you through. There are log base 6. There's 2 of them on the left. There's none of them on the right. Let me show you how to do that. Then I have this one, log of x plus log of x plus 3 on the left equals 1. Let me show you how to do that. But do you see what I mean? There's multiple logs on either side. And then take a look at this guy. There's 2 logs on the left and 1 log on the right. What's up with that? And then last but not least, I got this one too. So the thing is, when you're trying to solve a log equation, there are 3 Roman numerals in this lesson. The first Roman numeral was you got a single log on one side. Single log on one side, you attack it the way it says in the first section. Then, the second section I brought up, what happens if there's a log on both sides? Well, one log on both sides is different than this Roman numeral. This is the last thing that can happen to us. More than one log on either side. So here's what we do. We must use laws of logs to rewrite the equation. Here's what I mean. I did not have you guys go through all those log properties and all those log laws because we never talk about them again. We use them all the time to solve stuff. So, do you guys see, like, this is a subtraction? If I have log of something minus log of something else, I can rewrite it as a single log, but I would say this stuff divided by this stuff. I know you know this. When you are subtracting two logs, this is called the quotient law. I can rewrite it as division. That's the sneaky trick we use. Now, I go, hey, this is single log form. This resembles single log form. I'm going to double underline that thing because now I could do this if I want. I could do that. I totally could. Or I could just say base stays the base, flip-flop. What would it look like either way? If the base stays the base, and I flip-flop, I'd have 6 to the power of 1 equals this stuff. I would. Either way, I end up with, well, can I just call 6 to the first power? Can I just call that 6, guys? I'm going to erase that because it looks weird. And I like to make my brain happy, so I'm going to put a 1 under this, and then I'm going to say, dang, when I rewrote this as a single log equation, and I canceled this goop out, I got myself a proportion. I have a proportion to solve, and I know how to do that. I can cross multiply. I'm going back to my unit 3 rational stuff. So I go 6 times 2x plus 3. Well, that's 12x plus 18 if I multiply that, equals x plus 1. I'm going to get x's on one side, and then I'm going to get number on the other. So if I do that, I'll end up with what? 11x plus 18 equals 1. I already know I don't have to finish this problem because it's not going to work. See, this is an extraneous solution. 11x equals negative 17, and then I divide and I get x equals negative 17 elevenths. And I don't like ugly fractions like that, but you know what? That's not why I'm saying there's no solution to this. There is absolutely no solution to this equation. And the reason is real simple. And it comes from day one. Day one. Can we take the log of a negative number? And the answer is no, we cannot. So if I plug negative 17 elevenths in here, well, I would get the log of negative 17 elevenths plus 1, which is 11 elevenths. That would be a grand total of negative 6 elevenths. I can't take the log of negative 6 elevenths. I can't take the log of negative anything. All it has to do is ruin any part of your original statement, and that is a bad answer. Okay? And if I plugged it in here, you know, you could verify that right there it would ruin the party also. All it has to do is ruin it in one location. Now, this answer is possible. Now, let me blow your mind a little bit. I'm going to scroll up because I didn't say anything about this. Are these answers valid? Maybe one of them is right and the other one's wrong. Huh? What about this? Maybe, ooh, that guy's negative. Maybe he's bad. Huh? Maybe I should worry about all my answers that turn out to be negative. So let me show you this because I don't want anyone to jump the gun on me. Let's focus on this equation here. Before I messed with this one, I'm going to get rid of my monkey sound. I do like to say that though. I'm going to plug negative 1 back in, as if I had just solved it and I got negative 1 for an answer. Now, if I plug negative 1 in, I would square it. So negative 1 squared is 1. Can I take the natural log of 1? The answer is yes, I can. So this side is still valid. Then, on the other side, 5 times negative 1 is negative 5, plus 6 more, well, that would be 1. I can take the natural log of 1. So if I plug this answer back in, It's valid. It's okay. Not all negative answers are bad answers. In fact, if you want to, you could plug 6 in. You could verify that on one side it'll say natural log of 36, and on the other side it'll say natural log of 36. Both of these answers are legit. Both of these are correct. So here is the grand rule for all logarithmic equations. You should always plug them back in to check them to see if they're valid when you're taking the log of a variable. When you're taking the log of some variable, you want to make sure that your answer that you found is legit. So, let me just go through that one more time. I'm going to erase my work. The 3. Okay, I'm milking that joke. If I plug a 2 in to this, I would get 2 squared, that's 4. If I plug a 2 in for this, I would get 5 times 2 is 10. 10 minus 6 is 4. So this is a valid answer. I leave it up to you. You could plug that one in and double check and find out, is 3 valid? These are both good answers. So in log world, you can have one answer, 2 answers, or sometimes you get no solution. Remember, this is just a fancy way to say no solution. I just am lazy, so I like to use the mathematical symbols that allow me to be lazy. Now, let's take a look at this guy. And you might say, well, okay, I have a log statement plus another log statement. So if I'm adding 2 logs, we called this one the product law. Remember, there were 3 laws: the power, the product, and the quotient. So when it's a product, we can rewrite it so it says this one times this one. So did I get it to look like single log form? Yes, I did. Now, you might look at this for a little while until you see it, but what's the base? What's the base? I'll give you a hint if you need it. It's called the common log. I'll give you another hint if you need it. It's the button on your calculator is programmed to understand this base. You can write it in as a 10 if it helps your brain. And then I could say base stays the base flip-flop, or I could raise both sides with the base of 10. Either way, I would get it to say this. This would be the statement I'm looking for. Sure it would be, because this would be base stays the base, flip-flop, and that's how you convert a log into an exponential statement. And then, hey, it doesn't matter which side this is on. If it equals this, it equals this. So let's clean this baby up. I'm going to get x squared plus 3x equals 10. What the heck? I'm going to move that 10 over. And then I go, hey, I wonder if this thing factors. And I'm going to try x and x. And I get a plus, I think it's plus 5 minus 2. And then I go, hey, you know what? Minus 5 is a horrible answer. This guy is bad news, because I can see it right off the bat. I go back to my original problem. If I put a negative 5 here, I can't take the log of negative 5, but I could take the log of 2. That's legit. So in this case, the only answer that worked was 2. Once again, log equations. It's either 1, 2, or none. That's what happens when you're solving them. So what about this guy? I want you to look at this for just a second and try to figure out, why is this one a little bit different than the other ones? On this one, I have 2 logs on the left, 1 log on the right. Hey, look at this original. I had 2 logs on the left, no log on the right. This original, 2 logs on the left, no logs on the right. So what is the Roman numeral 3? How did I phrase this? There's more than 1 log on either side. you got to use laws of logs, that's the quotient rule or the product rule, to rewrite the equation so that it resembles single log form. And this is the most frequently broken rule, so be careful. I want to show you why somebody's going to get this wrong. And this is automatic. I marked this wrong on the test. You do this to me on the test, I don't even look to see if you did anything else right, because this is the biggest no-no in the world mathematically. Let me show you this is wrong. I will use a different color. How about blue? Somebody does this to me every single year. I did everybody with a base of 5. The problem is I did it 2 times on the left-hand side. I did it 1 time on the right-hand side. Doesn't matter, even if it evened out. You have to condense it into single log form. This will always be wrong. This is the most frequently done thing. No. Please, whatever you do, do not do this. Okay, I'm going to get rid of my big no please. I'm going to get this out of my way. I want to get rid of all my 5s here that I wrote in. Whoop, and I got rid of a little bit of the word log. That's okay, I'm going back to black pen. Bam. Here's what I'm going to do. I'm going to say this is a product. This will be log base 5 of 6 times 3x minus 1. I am using the product law. If it was a minus, I would be using the quotient law. But I'm not. So here we go. Log base 5 of 6 times 3x minus 1. What does it equal? Well, I haven't even messed with the other side, because the other side was just sitting there waiting for me to get it to this point. And now I go, dang, this is a single log on both sides. Single log on both sides. What do I do? Now I get to do this. Now I say I'm doing it 1 time on the left, 1 time on the right. That's all I'm going to do. And now it's going to work out for me. I get 6 times 3x minus 1 on this side. What's it equal? It equals 10x plus 7 on this side. Now, on this side, the parentheses are going to change things up a little bit. But on this side, there's nothing out here. There's a 1. So I could just take it out of the parentheses. Sometimes parentheses are overkill. And away we go. Let's bring this thing down. What do we have? We have 8x. I'm going to move the 6 to the other side. And it's going to be equals 13. I'm going to divide by 8. And I get x equals 13/8. Now 13/8 is not the prettiest number I've ever met in my life, but here's what we care about. If I were to plug 13/8 back into the original, 3 is a positive number. 13/8 is a positive number. If I multiply those two guys together, they're positive, and they're also way bigger than 1. So 3 times 13/8 minus 1, this whole side's still going to be positive. We're okay. And this is positive. 10 times that plus 7 is all positive. So the thing is, this answer may not be the prettiest number I've ever seen in my life. But it is a legit answer, because when I plug it back into the original, it does not cause a 0 or a negative value. I hope I'm hammering that thing home for you, because I got one last problem, and I want you to see it, and I want you to try it. So here it is. I've got 2 logs on one side, and I got 1 log on the other, but I definitely don't want to do e on the left and then e on the right. I don't want to do that. That is a bad thing, and I automatically just mark it 0. That's wrong, and I go to the next problem to grade. Please don't do it. I look for it in the homework too. It is the most broken rule I find every year. So what am I going to do instead? Well, I'm going to tell you, pause it. See if you can do it. And then hit play, and you'll see me go through it. And let's see if we both end up with the same answer. Shall we? Okay, so pause it and do it. No, really, pause it. Okay, I thought that was funny. No, really, pause it. Okay, I hope you're back after you did it, because if not, you didn't pause it. But I'm not going to make the same joke again, even though it's hilarious. I am, however, going to treat this like a product on that side. And I'm going to do this one over here. And I am going to say unto this, now it's now it's monkey time. And I get 5x minus 2. What does it equal? It equals, well, x times x plus 2, which means distribute. It doesn't mean divide everything by x or make up your own rules. I'm going to get this to look like that, which means I have a quadratic. The highest power is currently positive, so I am going to move all this stuff over to the other side. I'm going to move it. I'm going to move it, because I like to move it. And then I get x squared minus 3x plus 2. What's it equal? It equals 0, because I got everything on one side. So let's factor this thing, and I think it's going to be pretty easy, because I got x, and it looks like minus 1, minus 2. So I have one answer that should be 1. I have one answer that should be 2. But if you have paused this, worked through this problem and everything, what I want to know from you is, are they both legit? Is only one of them legit? Or is none of it legit? And you have to plug it back into the original statement before you messed with it. And if you do plug those answers in, they are both good guys. These are both valid answers. So, if you were to practice this skill, I would hope you'd know that to solve a log equation, we try to get it into a point where we use an exponential conversion or formula or property to get rid of the log. Then we can solve it. And I'm just scrolling through this slowly because I want to make sure. There's 3 different Roman numerals I came up with. We just talked about this one. And then, don't forget, sometimes the original problem has a single log on both sides to begin with, and we try to cancel out the logs by doing that. And then, of course, we started back here with, sometimes it's just a property you're staring at. Sometimes it's a mini equation you're staring at. And if it's a mini equation, you're either going to convert it with this technique or convert it by doing base stays to base flip-flop. Same thing goes with this one, but don't be fooled here. That's just punch it into your calculator, because you can trick your calculator into being base 5. And if none of that seems to work, then we try to cancel out the logs. That's a lot of work. That is. But I want you to practice it. And since tomorrow is the last new lesson, well, maybe it's not tomorrow. Tomorrow. Or the next lesson. Let's put it that way, because the next lesson will have inverse functions. So here's what I did. This contains some mixed practice, some review. So guess what? This is just practice with the laws of logarithms right there. This is also practice just with the laws of logarithms right there. But then I wanted to mix this up. Here it says solve the following log or exponential equations. So remember, we have 2 types of equations out there now. We have those that begin with the word log in them, and if they do, we try to get rid of the word log in them. Then we have the other kind that start with exponential look, And sometimes to solve those, we have to introduce the log into it, because log equations can be defeated by using exponential techniques, and exponentials can be defeated by using logs. Unless, and here's the last thing, unless you don't need to touch a log at all. So I'm just going to show you number 14. Please take a look at number 14 right there. That's an exponential equation. But they already have the same base. You do not have to go crazy on that. You can just say, hey, you guys have the same base. I'm going to set your powers equal and go to work. That's what I'm going to do. Now, there's those problems. So like I said, this is review. It's going to be on your unit test. This is review, going to be on your unit test. This is a mixture of exponential equations and the topic we just covered, but it goes to 40. Check this out. You think you guys have fun on the weekends? No way. I'm sitting around making up all kinds of equations for you to play with and try. And then you think it's bad, like I got to do 40 of these? Well, guess what? This answer key didn't make itself. I had to make this answer key, so I had to do this. But I did not have any whiteout, so when I wrote this in the wrong spot, I crossed it out with my pen. All right? So guys, here's the answer key. Please check your work. And then the very next lesson is our last lesson. It is inverse functions. So please pause it, take a picture of this. I'm going to scroll back up for you. There's 21 to 40. Take a picture of it. And there's 1 through 20. Take a picture of it. All right? And then we're one lesson away from finishing this unit. Wonderful. All right. Have a good day.